Have you ever just watched fireflies on a summer night? It's pretty magical. Well, tonight, we're going to pull back the curtain on one of nature's most amazing light shows and really dig into the science behind that incredible glow. So here's the big question, right? How on earth does a living, breathing creature create light that's nearly perfect, with almost no heat? I mean, we're talking about what scientists call cold light. It's this incredible feat of biological engineering, a light so efficient it just blows our own tech right out of the water. So how do they pull it off? All right, to get that answer, we need to zoom in, and I mean way in. We're going down to the microscopic level, right inside the firefly's abdomen. Let's get into the engine room, the chemical lantern itself. Now, the fancy scientific name for this whole process is bioluminescence. And what's so important to get here is that this is not like something that glows in the dark after you shine a light on it. No. Fireflies create light completely from scratch, just through a chemical reaction. It's a totally self-contained power source. Okay, so let's break down the recipe for this glow. It all starts with a chemical, a substrate called D-luciferin. First, that stuff combines with ATP, the energy molecule in basically all living cells. Then, an enzyme called luciferase jumps in to speed things up, creating the super high energy intermediate. Next up, that intermediate gets hit with oxygen, and boom, this creates an unstable chemical ring that immediately breaks down, releasing all that stored energy. But here's the magic. It doesn't release it as heat. Nope. It releases it as a photon, a tiny particle of pure light. And to really put that into perspective, just look at this comparison. Think about an old school incandescent light bulb. It wastes about 90% of its energy just making heat. A firefly? It converts almost all of its chemical energy, we're talking like 96%, directly into light. It is almost perfectly efficient. I mean, Thomas Edison would have been incredibly jealous. Okay, so we've got the chemistry down, but that just opens up a whole new can of worms, another puzzle. If the chemical reaction is the engine, how does the firefly actually become the driver? How does it get that super precise, rapid-fire control over its flashes? Yeah, this is a really good question. All the ingredients, the luciferin and luciferase, they're just sitting there, ready to go at a moment's notice. So what's acting as the light switch? Being able to control a chemical reaction with that kind of speed is just an amazing biological trick. And you know what? The answer is so simple, it's beautiful. It's not about slowly making more chemicals. It's all about controlling the supply of that one last crucial ingredient. The secret isn't in the fuel tank. It's in the pipes that deliver the oxygen. It's all about plumbing. So check this out. Normally, inside the firefly's light cells, the mitochondria are like these tiny oxygen sponges, just soaking it all up. But then, a nerve signal fires and it releases nitric oxide gas. This gas instantly tells the mitochondria, hey, take a break. With those little sponges temporarily turned off, oxygen floods the cell, hits those chemicals we talked about, and flash, you get light. Then, as the nitric oxide disappears, the mitochondria turn back on, the oxygen vanishes, and the light goes out. It's an unbelievably clever on-off switch. So now that we get the how, let's zoom back out and talk about the why. Because these flashes aren't just random. Nope. They're a really sophisticated, totally silent language that these insects use to talk to each other in the dark. Biologists call this whole thing a photic dialogue. You've got the flying males, and they're broadcasting their own special code. If a female on the ground likes his style, she'll flash back a very specific answer. It's a full-on conversation where every single pulse, every pause, it all means something. And the diversity here is just mind-blowing. Take the common firefly, Photinus spiralis. He actually traces a J shape in the air. Then you have the blue ghost, which gives off this long, continuous, kind of spooky glow. And of course, the famous synchronous fireflies, Photinus carolinus, that get together in massive groups and flash all at once. It's breathtaking. Each pattern is like a different radio channel, making sure nobody gets their signals crossed in a busy forest. But this language of light, which is so often about finding a partner, it has a dark side, a really dark side. In the world of fireflies, that beautiful communication can be twisted into a deadly weapon. Yeah, for some poor, unlucky males, the flash that they think is promising them a mate is actually luring them to their doom. The strategy is called aggressive mimicry, and in the firefly world, the absolute masters of this dark art are from the genus Photurus. See, they've learned to speak other fireflies' languages perfectly. So picture this.
You've got a male photonous firefly, and he's flashing his hopeful little signal through the night. Down below, a female flashes back with the exact, perfectly timed response he's waiting for. He's thinking, this is it. He flies down expecting to find a mate, but instead he finds a predatory photorous female, and she immediately grabs him and eats him.
I mean, it's a brilliant strategy, right? If a little brutal. See, this photorous female, she can't make her own defensive chemicals, these things called lucifobadegens. But the poor photonous male she just tricked, he's full of them. So by eating him, she gets a 2-for-1 deal. She gets a meal, and she literally steals his chemical armor, using those toxins to protect herself and even her eggs from predators like spiders or birds. It's just wild. Now, this whole complicated system of communication and, well, deadly deception didn't just pop up overnight. The evolution of the firefly's glow is an incredible story of how one simple biological trait can be reshaped over millions of years for completely new jobs. So the latest science suggests the glow probably didn't even start as a signal. Way back, like 136 million years ago, it might have just been an accidental byproduct of a chemical reaction that helped insects deal with more oxygen in the air. It was only later that this accidental glow was repurposed by their larvae as a sort of "don't eat me" warning sign. Then some species actually evolved toxins to back up that warning. And finally, much later, it became the super complex language for finding a mate that we see in the adults today. What a journey! And this whole story, from a simple chemical quirk to this complex language, isn't just fascinating trivia. The Firefly's living lantern actually holds lessons that are directly inspiring our own technology and really shaping our future. It turns out it's not just the chemistry that's so ridiculously efficient. The actual physical structure of the Firefly's lantern is perfectly designed to get as much light out as possible. And by studying it, we're figuring out how to build better lights ourselves. Get this. By creating a layer on top of a normal LED that copies the jagged, microscopic scales on a Firefly's lantern, scientists boosted its efficiency by a whopping 55%. That is a huge deal. It's a powerful lesson from nature that we applied directly to our own tech. And that kind of brings us full circle to a final, really important thought. As we've gotten better and better at lighting up our own world, are we accidentally drowning out theirs? All of our artificial light pollution, it messes up their mating signals. Habitat loss is threatening their survival. You know, the Firefly engineered a near-perfect light, a gift of evolution we are only just starting to truly appreciate. The real question is, are we going to be wise enough to make sure we don't put that light out for good?
Don't forget to like and subscribe for more How Meets History.